Good morning, class. This is Mr. Roberts. Yesterday in class, we discussed reflections, and today we're going to extend that and see how we can get to our other two rigid transformations using just reflections. There are a total of three rigid transformations. We have translations, reflections, and rotations. And using reflections will allow us to get to the other two. A beautiful triangle here, and there's a particular vertex that we're going to track. It's located right here, and it has a coordinate where x is -2 and y is +4. And what we're going to do is just take this and reflect the entire Cartesian coordinate plane across this thing we call the y-axis. And when I do that, this particular shape will move over here, and this point is the image of the original point. So we can say if this was point A, we would call this A prime, which means that it's the imaging point. It's the point that's imaged from A, and it's located at the point 2, 4. Now, if we do that for a lot, we get to where we observe the following relationship. If we are going to do a reflect or a reflection across the y-axis, it appears that any xy point we have will simply translate to or become the opposite x value, and y will stay the same. So in the case here, you can see we had x was -2, and then the opposite of that -2 is +2, and my y values both stayed equal to 4. And another thing we considered was reflections across this line, x equals y. So this is the line, or we can say y is equal to x. So obviously if I graph this line, I know that this line has a slope of up 1 unit over 1 unit, and it has a y-intercept of 0. So when I say I'm graphing the line y equals x, this is what we mean. We begin here at the origin, and then we just follow the up 1 over 1 pattern. When I reflect across that, there's another thing that we observed yesterday, and we'll just track this particular point. If I have the point here where this is the point where x is 1 and y is 2, right? X is 1, y is 2 is located here. When I reflect across the line x equals y, notice what happens. X becomes the number 2 and y becomes 1. So my x and y is just simply switched places, right? So if we want to reflect, or a reflection across the line x or y equals x, any xy point is going to be mapped to a point where x becomes the y value and y becomes the x value. So now let's consider what happens if we do multiple reflections. First across parallel lines, and then across a line and a line that is forms a 45-degree angle with the other line. So if we have two parallel lines, and I'm just going to say that these two lines that you see on the screen are parallel to each other, and we often show the fact that lines are parallel by including some of these triangle things on it, so like this and this. Those arrows there oops, I keep erasing them. Those arrows indicate that these two lines are parallel to each other. If I reflect across one line, right, I would get this shape. And you can observe a couple of things here, right? Every single point is exactly the same distance. It is exactly the same distance from the original. So this image point right here is 1 unit away, and you can see right here it's 1 unit away also. So that's an idea, like when you reflect across a line, every single point that's in the image, right, this is the image, and we'll say this is the original. A gets mapped to a point that's equidistant from the original. Now I'm going to do this again. I'm going to take this second object, this A prime, and I'm going to reflect it across the line that was parallel. And when I do that, I get this shape, right? So now you can see we had our A, and then this is point A prime right there. And then when we reflect it again, this is point A double prime. And this distance, right, from here to here, I don't know what it is, I'll just say this distance is C, is going to equal the same distance from here to here. This will also be the distance of C. Now the interesting thing about that is when I reflect an object twice across parallel lines, that's equivalent to a translation. So 2 reflections across parallel lines is equivalent to a translation, and I can show this just by taking this point and sliding it over there. So you see that point that slides across like that is exactly the translation. So that's the one idea that I want to have first, is that this double reflection across parallel lines is equivalent to a translation. So we just saw how reflection across lines that are parallel to each other are equivalent to a translation. And now I want to look at how reflecting across lines that are, I guess they form a 45-degree angle. So this angle right here is 45 degrees. And there's a couple points we want to check. That looks like I wrote 450 degrees. This is a 45-degree angle. So if I track the tip of this finger, and I'll call this A, and I reflect across this blue line, I end up getting this first image point, A prime. Now I'm going to do the same thing again, and one of the most difficult things yesterday for us was reflecting across these lines that were diagonal. I think question 3 and 4. So this is equivalent to the line y equals x, and if I think about this in a Cartesian coordinate plane system, the x and y's are going to switch places for each other. Well, if I think about this, I can go over 1 unit, right, over 1 unit, and then I can go up a total of 11 units. So from this point that I'm going to rotate about, it's going to be equivalent to my center of rotation, I go over 1 unit and then up 11 units. Well, if I flip the order, and instead of going up 1 over 11, I go over 11 units and then up 1, right, I end up getting this point. And this point is I'll call it A double prime. So what happens is I'm reflecting across this line, and every single point that I have gets mapped using essentially the same rule that we have when we map across the line y equals x. Now this is equivalent to a 90-degree rotation about the point where these two lines meet. So where these two lines meet, I can rotate 90 degrees about that point, and I get the exact same shape, there it is, as I do when I do this double reflection, one across a line and then another one across a line that makes a 45-degree angle with the other line. So to quickly summarize, if we have 2 parallel lines and I reflect across one and then the other, the resulting image that I get is the same image I would get as if I just simply took the original image and I translated it that distance across. Something similar happens when we look at translations across lines that meet at 45 degrees. So if I take this image and I place it in GeoGebra, you can see I do the reflection, this little part right here with the shadow by the nose, it's further away, and then that's actually not the shadow by the nose, this is the shadow by the ear. It gets reflected way over to here, and then that gets reflected to right over here. And when I do that, that's equivalent to a 90-degree rotation. So if I come in and grab my rotation tool, I can rotate this 90 degrees. And when I'm done, they will line up perfectly. So, in summary, reflections about the y-axis can be achieved by mapping points xy to the opposite of xy. Reflections about the x-axis can be achieved by mapping the points xy to the point x, the opposite of y. And reflections over the line y equals x are achieved by mapping points xy to the point yx. Reflections across parallel lines are equivalent to a translation. And reflections across lines that intersect results in a rotation. So what's interesting about that is that we have three rigid transformations. The rigid transformations are reflections, translations, and rotations, and those can all be achieved by just using reflections, because with using two reflections I can either get a translation, or with two reflections I can get a rotation, depending on the nature of the lines that I'm reflecting across. If they're parallel, I get a translation. If the lines meet, I get a rotation where the point where they meet is actually my center of rotation. So reflections, translations, and rotations are rigid transformations. Rigid transformations, that means that the size and shape of the object being translated does not change. Right, that's it for today.